Hi everyone, welcome to this video on the topic of graph coloring. We'll start with the following scenario. Suppose you draw a curve without lifting your pencil from the paper, intersecting as many times as you want until you have returned to the starting point. The curve that you draw can intersect and cross itself any number of times. Now, what is the minimum number of colors needed to color this drawing if like colors can only touch at one point? So the curve that you draw might end up looking something like one of these. So let's do a quick coloring of a couple of these to get a feel for how this works. Okay, here are two such drawings. And we'll focus first on Swirl Town. So we pick a region and assign it a color. Now, notice the region that we have here, because it touches the region along an edge, it's going to need a different color. However, the region that we see here, that one can have the same color yellow because it only touches our other yellow region at a single point as opposed to an edge. We can continue this and color all of the regions that we like that are valid to be the color yellow, and then return to our original blue color, coloring all of the regions that we see here. We just have to make sure that any regions that connect with an edge receive different colors. Now, this particular doodle of Swirl Town can be colored using only two colors. What about in Boxville? So we'll pick a starting region and give it a color. The region up here can also be red since it only touches our original red at a single point. All right, but this guy is going to need a different color, as is this one. And now what about the region that we have up top? This region here, because it touches both red and a blue region along an edge, that's going to need a third color. So for that region, we'll need to introduce a third color, color yellow. So we can continue on in this matter, and the idea is to use the fewest number of colors that we possibly can, but we have to make sure that any region that's connected by an edge receives a different color. So for example, this region here, it touches both a red and a blue with an edge, so it would need our third color of yellow, similarly for this region here. So the particular doodle of Boxville is going to require us to use three different colors in order to get what we would call a valid coloring. So you may take a moment and see what you get for the own little region that you drew, or for the examples of Bumpington or Popdale. What's the fewest number of colors you can get away with and give a valid coloring of these regions? It turns out that map coloring is a profound mathematical topic with many multi-million-dollar industrial applications. Scheduling, assigning frequencies to mobile radios and other users of the electromagnetic spectrum, and conflict resolution. Now, it's important to be able to tell different neighborhoods apart from a distance. So if two neighborhoods or regions share a boundary, an edge, they must be colored different colors. So the graph that we see on the top is colored well. Notice that when two regions touch at a single point, they can be colored the same color. The coloring on the bottom is colored badly. There are two blue regions that share a boundary, and therefore they should be given different colors. Now, there are two basic strategies one might use. One is called the polka dot strategy. It's a greedy algorithm. You use one color to exhaustion, and then go back and try color number two, so on and so forth. Our second option is a chain of logical deductions. One region is colored red, and then our regions that touch red are colored blue. Those bordering blue would be colored red, so on and so forth. And if you don't happen to have nice crayons or markers handy, you can always just use numbers in the regions to represent different colors. The basic question is, How many colors do you need so that countries that share a boundary line are not colored the same color? This minimum color in graph theory is called the chromatic number of our graph. Now in 1852, cartographer Francis Guthrie conjectured that 4 colors were sufficient. He brought this idea to his brother, who happened to be a mathematician. They began to work on this problem, and it was eventually proven that he was right. In the case of a map, 4 colors is the minimum number required. But this result wasn't actually proven until 1976, and it was the first mathematical theorem that was proven using a computer. Now, what does this have to do with graphs? Well, we want to take an organized, a logical, a mathematical approach to map coloring. And so what we're going to first do is translate our map into a graph. So given a map, we'll draw a vertex for each country and an edge between vertices if the countries share a common boundary. Keep in mind, the graph is a representation of the original map, but is not the map itself. Here's an example. Here we see a map with 5 regions, A through E. We want to take this map and translate it into a graph. So each one of our countries or land masses will be represented by a vertex. Here they are, A through E. Now, we're going to connect the vertices in our graph with an edge if our countries share a boundary. So, looking at our map, we see that region A shares a boundary with regions D and B. And therefore, in our graph, we'll connect vertex A with vertices D and B using an edge. Now let's focus on region B of our map. B not only shares a boundary with A, it also shares a boundary with D, E, and C. So we need edges connecting vertex B to the vertices D, E, and C. Now, who does C also share a boundary with? Region C also shares a boundary with regions D and E. So we need those edges in our graph. Finally, region D shares a boundary with E, so we need to have an edge connecting vertices D and E as well. Now for our coloring, we're going to focus on our graph and color the vertices of our graph. Now, any 2 vertices that are connected by an edge must have different colors. So let's pick a color for vertex A to get us started. How about blue? Now, since A and B share an edge, they must receive different colors. So we'll pick a different color for vertex B. I picked green. Now, what about D? Well, D cannot be blue because it shares an edge with A. And D cannot be green because it shares an edge with B. So we need a third color for vertex D. I picked yellow. What about vertex C? Vertex C cannot be yellow or green, but it can be blue. So we're able to reuse our original color of blue. Because vertices A and C do not share an edge, then they are allowed to have the same color. All right, finally, what about vertex E? It cannot be yellow, blue, or green since it's connected to vertices D, C, and E. Therefore, we will need a fourth color for vertex E. I picked orange. Okay, so we've now done a graph coloring. Notice, any 2 vertices that share an edge must have different colors. And we can see how this would give us an answer to our map coloring by translating the color of the vertex to the color of the region that that vertex represented. So we do have a valid map coloring. Great, don't worry, we're going to do more examples in just a moment. First, some terminology. A vertex coloring. The vertex coloring problem for a graph requires assigning each vertex of the graph a color or a label such that 2 vertices joined by an edge are assigned different colors. keep in mind, if you don't have colors available, you can just label them with a number. Number 1, number 2, number 3, etc. The chromatic number is the minimum number of colors needed to label the vertices of a graph so that no two vertices of the graph joined by an edge get the same color. And Brooks' theorem says that if a graph has no valence greater than n, then it can be colored with n or fewer colors. Now, here's something to keep in mind. We said that in the case of a map, 4 colors was always sufficient. A warning, that will not be true in the case of a graph. When we are coloring the vertices of a graph, we may need 5, 6, 7, or more colors. Here are some examples. Let's look at the following graphs and see if we are able to color them with 3 colors. Will we need 4? What is the chromatic number of the graph? Let's do a couple together, and then I'll let you practice some on your own. All right, we'll start with the graph that we see here. We'll pick a vertex and give it a color. Now, in this particular graph, the vertices that are connected to it will need a different color. But notice, because none of these vertices are connected to each other, then they all can receive the same color. We move on from here and continue to go. So we see that in the end, we're able to get away with 2 colors. Note, no 2 vertices that are connected by an edge have the same color. And so the chromatic number, which we represent with the Greek letter chi, it looks like a really fancy X. The chromatic number of this graph is 2. All right, what about the next one? We pick a vertex and give it a color. All right, this vertex is connected to it, so it receives a different color. And now because this vertex is connected to both a blue and a green, it's going to receive a 3rd color of orange. Let's work on this bottom square. We're allowed here to reuse green since it's not connected to our green vertex. Oh, but this one is touching both green, blue, and orange, so it must receive a 4th color of purple. We'll continue on. We'll reuse blue, then we can reuse green, back to purple, and then orange. So we used 4 colors for this graph, and so the chromatic number for this graph is 4. All right, what do you think for the next one? This one is a complete graph on 6 vertices. And by complete graph, I just mean that every 2 pair of vertices is connected by an edge. So since it's a complete graph on 6 vertices, we're going to need 6 different colors. All right, what do you think about graph H? You may want to pause the video and try that one on your own before I reveal an answer. So for graph H, we would need 3 different colors. And now what about the bottom row? Again, I encourage you to pause the video. I'll then reveal the chromatic numbers. So we have chromatic numbers of 5, 2, 2, and 5. And here are valid colorings using the chromatic number I suggested. Great. All right, so this is all for our introduction to the topic of graph coloring. In our next video, we're going to apply this to the real-world problem of scheduling. And I look forward to seeing you there. Thanks, guys.